Hello, welcome to the next video lesson. This one is on electrochemical series, and you may remember way back in GCSE that you did the reactivity series, and this is not dissimilar, except what we do here is we order all of the species, which might be metals or non-metals or molecular ions. We order them all according to their electrode potential, and we put the most negative electrode potential at the top, and we put the most positive electrode potential at the bottom, and we order them all in a series so that we can see what's most reactive and what's less reactive. And we can also use that series to calculate the EMF of a cell. And here we have the learning objectives. The first one being that we want to know that standard electrode potentials can be listed as an electrochemical series in order of electrode potential. And also we want to be able to use those standard electrode potentials to predict the direction of simple redox reactions and to calculate the EMF of a cell. So let's get on with it. But first, let's consider some evidence for electron transfer, and it gives us the opportunity to review some philosophy of science. So redox reactions involve the transfer of electrons from one substance to another, or so the theory goes. But you might wonder how anyone knows this, because you can't see the electrons move. Well, that's where the philosophy of science comes in. Because what you can do is you can use the theory to make a prediction, and then you can test the prediction with an experiment. So if we start off with a theory, right, we can use that theory to make a prediction, and you can then test that prediction with an experiment. And lots of science advances this way. So our theory, for example, in this case, is that redox reactions involve the transfer of electrons from one substance to another. So let's just write that down. Redox reaction, transfer of electrons. Okay, so if we've got a theory, then we could make a prediction from that theory. You could predict that a current will flow between the electrodes of an electrochemical cell. And if the oxidation reactions happens at one electrode and a reduction reaction happens at the other electrode, then you might get a flow of current. So that's our prediction. Flow of current between electrodes, where one electrode an oxidation reaction happens, and at the second electrode a reduction reaction happens. So if we predict that a current will flow when we get these reactions happening at the electrodes, then that might support our theory that redox reactions involve the transfer of electrons. So then, of course, what we might do is we might set up two half cells with two electrodes of metals in their solutions. We might have a salt bridge, and we might connect this to a circuit. And the ammeter might read a current, and if so, that current has tested. What we've done is we've tested with this experiment here that current flows between these two electrodes in the apparatus, and that therefore has supported our theory. Of course, the experiment doesn't prove a theory. You can only disprove a theory with an experiment. So if, for example, you set this rig up and you got no current, then you could be pretty sure that the theory was wrong. And actually science progresses quite often, or in fact most often, by falsification. And so that's an experiment that disproves a current theory. So when a current theory is disproved by falsification using an experiment, then the scientists have to adjust their theory, come up with a new hypothesis and prediction, and test that with new experiments. And so you get a gradual evolution of the theories like that. And basically this theory, that redox reactions involve a transfer of electrons, hasn't been disproved yet, so it's pretty likely that it's true. And for now, that's a theory that chemists are sticking to, because it's one, it's pretty likely, and two, it's been supported by all the experiments that's been done on it, and it's never been falsified by an experiment. Okay, I hope you enjoyed that little bit of philosophy of science, but let's carry on. And first of all, what we can do is we can define an electrochemical series. And basically all it is a long list of electrode potentials for different electrochemical half cells. And here we have one here. So that obviously there's a selection of half cells here, commonly used half cells, but you'll see some electrochemical series with many more half cells on them. So there's a few things to notice about the electrochemical series. The first is that they're ordered. At the top we have the most negative electrode potentials, and at the bottom we have the most positive electrode potentials. There's, of course, it's hydrogen roughly in the middle, because we've said hydrogen is zero by definition. And so the ones with the most negative electrode potentials are going to be the reactive metals, the metals that are least electronegative, or the most electropositive. So group 1 metals, group 2 metals, for example. And the ones at the bottom, the ones with the most positive electrode potentials, will be the most reactive non-metals. You'll see chlorine down at the bottom here, and manganate, also a very strong oxidizing agent. So obviously the group 7 compounds will be near at the bottom. There's bromine quite near the bottom as well. Dichromate, another strong oxidizing agent. So there they are, the most reactive non-metals at the bottom, the most reactive metals at the top. And the second thing to notice is that all of the reactions are listed as equilibrium reactions. Of course they are. So I'm just underlining the magnesium equilibrium equation here to emphasize that. But you'll notice that they're all written in the reduction direction, with reduction as the forward direction. That's just standard procedure, and that's unusual. Sometimes you might think that it would be unusual for magnesium, and it would be, because usually magnesium, if magnesium solid was one electrode, it would usually oxidize to make magnesium ions, and so the reaction would be most likely to go in the oxidation direction, the one that I'm drawing just now. However, it is convention that we write all of the equations as reduction reactions, and they're all equilibrium reactions. And while we're here, why don't we have a reminder that when we put two half cells together, then the one with the most negative electrode potential, right, is going to be the oxidation reaction, and the one with the most positive electrode potential is going to be it's just going to go in the direction of the reduction. So say, for example, we had magnesium and iron, for example, as two electrodes. You would have magnesium going to magnesium ions, and you'd have well, let's use silver, for example. You'd have silver and silver solid. And that would be the reduction reaction on the right hand side, and this would be the oxidation reaction on the left hand side. And there's actually a little mnemonic that can help you remember that, and it is no PR. No PR. Presumably meaning no public relations. And what that stands for is most negative electrode potential and that stands for oxidation, and then this would be the most positive electrode potential, and that would stand for reduction. So when you were looking at the oxidation reaction, you would actually write it down in the reverse direction, like we did with magnesium. You would write the magnesium as magnesium solid. This goes to magnesium 2 plus ions plus 2 electrons. If you were having to write that little half equation down, so it's the opposite direction to the one that's given in the electrochemical series. But when you write the reduction half equation down, you're just writing it down in the direction that it's given to you in the table of the electrochemical series. Okay, I hope that's clear. Okay, the next part of the video lesson is predicting the outcome of reactions. And you might be given a question about a reaction such as, will zinc react with aqueous copper ions? Or, for example, you might be given, will silver react with aqueous magnesium ions? So that's what we mean by this sort of reaction. It's a redox reaction, and we have to predict yes or no whether the reaction that we've been given will happen or not. So there are several ways of doing this. One of which is called the anti-clockwise rule. It's a mechanical way. I prefer another way, a more intuitive way, but let me go through the mechanical way with you first. So if you don't get the intuitive way, you can always use this as a fallback. So let's use an example as we go through. So that first question that I listed out there, will zinc react with aqueous copper ions? There's our question. So this is going to be zinc solid, and aqueous copper ions are going to be Cu2 plus ions in solution. Right, so is the zinc solid going to react with the copper ions? That's the question. And the first thing we have to do is we have to write down the two half equations for the redox reaction. Okay, so as far as zinc is concerned, let's put zinc in blue. Okay, so as far as zinc is concerned, it's going to be zinc, the half equation written in the reduction direction is zinc 2 plus aqueous is going to accept 2 electrons, and you're going to end up with zinc. And then if we do the same for copper, let's do copper in red. Okay, and in the reduction direction we would start off with copper aqueous ions, and they would also accept 2 electrons to form a copper metal. Okay, so we've got the two reduction reactions down. So at least the forward reaction is the reduction reaction for both zinc and copper. Then what we do is we would write down the electrode potential. So the electrode potential for zinc So you look at your electrochemical series and you see it written like this: zinc 2 plus to zinc solid, and that electrode potential you'll read off electrochemical series is minus 0.76 volts. And if you did the same for copper, you would see copper 2 plus and copper given an electrode potential of positive 0.34 volts. So that's what you would read off the electrochemical series. And then what you have to do with this anti-clockwise rule is you have to put the half equations, the half equation with the more negative electrode potential on top. Okay, so I'm going to move back to blue for zinc. So the one that is more negative is the zinc. So we're going to write that half equation on top. And they're both written still in the reduction direction. So we have zinc 2 plus aqueous plus 2 electrons it's in equilibrium with the zinc solid. Okay, and the other one is going to go on the bottom. So we've got copper 2 plus accepting 2 electrons in equilibrium with copper solid. Okay, so that's that step. Now the next step, which I'll do in purple, is to draw on these anti-clockwise arrows. Okay, so you go from the product of the top reaction to the reactant of the top reaction, like so. And then the bottom arrow, also going in the anti-clockwise direction, goes from the reactant of the bottom half equation to the product of the bottom half equation. So you see we've got 2 anti-clockwise arrows there. And then what you have to do is you have to look at the non-pointy ends, the starting ends of the arrows, to work out if the reaction would happen. So if we looked at the starting end of the arrows, we've got zinc and we've got copper 2 plus ions. So, and then we refer back to the question. What I've drawn in the boxes is what would react in this when these 2 half equations were put together. So in the question we've been asked about zinc solid. Does that react with copper ions that I've put in the squares there? So you can see that this will react. Zinc solid will react with copper ions. Okay, so yes is the answer to this question. Okay, so let's go through that once again with a different example. But this time let's use an alternative question. This time let's say, will silver react with aqueous magnesium ions? Okay, that's our question. So you'll remember the first step is to write down the 2 half equations. Okay, so the 2 half equations, first of all, silver. Okay, if we look at an electrochemical series, we've got Ag plus. Well, let's write it down as a half equation. So it's Ag plus 1 electron in equilibrium with silver metal. And as far as magnesium is concerned, we would have magnesium 2 plus ions plus 2 electrons in equilibrium with magnesium metal. Then we go to our electrochemical series to look up the electropotential of silver, and we would find this sort of listing for silver. It would come out at 0.08 volts, and for magnesium 2 plus magnesium metal would come out at minus 2.38 volts. Okay, so if you remember the next step is to write out the two half equations, one on top of the other, with the most negative one on top of the other one. So the most negative one is the magnesium. So let's write out the magnesium. Let me do that in red. Magnesium, and also I'll write it down here to give me some space. So the magnesium 2 plus 2 electrons is in equilibrium with magnesium solid. And then let's write the less negative one, in this case positive one. So you've got Ag silver ions in solution, and they might take an electron. If they did, they'd be in equilibrium with silver solid. Okay, so now we have to write on our anti-clockwise arrows. So we go from the product in the top reaction to our reactant in the top reaction. That's in the anti-clockwise direction. And we do the same for the, well, the opposite actually, for the bottom reaction. We go from the reactant to the product. And so what we find that will work is magnesium solid and silver ions. So those, the starting points of the arrows, the species at the starting point of the arrows, the ones that I've put in green squares there, are the ones that will react together. Right, so then we have to refer back to the question. The question was asking us about silver solid. Will that react with aqueous magnesium ions? So Mg2 plus ions, aqueous magnesium ions. And so we've got magnesium solid, not magnesium ions, and we've got silver ions, not solid silver. So the question, of course, is no. The answer to the question is no. The silver will not react with magnesium ions. So the last point to make about predicting the outcome of reactions, these redox reactions, is to not assume that the reaction is going to work. You're just as likely to be given a reaction that won't work in a question such as this. Yes, and you can also use the anti-clockwise rule to find the cell potential. And if I can just ask you to cast your minds back to remember the equation for the cell potential. And what you'll remember is that the standard electrode potential for the cell is the electrode potential right hand side, take electrode potential left hand side. That's the standard equation, and I actually prefer to remember it like this. For the reduction reaction minus the electrode potential for the oxidation reaction. And for the anti-clockwise rule, you can write out the same equation such as this. The electrode potential of the half equation that you write on the bottom, take the electrode potential of the half equation that you write on the top. and that's when you've gone through the process of putting the most negative half equation on top and the one with the less negative half electropotential on the bottom, in which case you come up with this equation here. So let's have a look at an example. If you were to look at an electrochemical cell consisting of zinc and copper, as we've seen quite a few times, the zinc would go on top because that's got the most negative electrode potential, and that, if you remember, is minus 0.76, and the electrode potential of the copper half cell is 0.34, so that would go on the bottom. So the electrode potential of that cell, according to this this version of the equation, would be the electrode potential of the bottom reaction, which would be 0.34 minus the one on top. And as we've worked out before, that comes out at plus 1.10 volts. And just for the sake of completeness, why don't we do one more example? Let's do an example of magnesium and aluminium. And when we look at the electrode potentials for magnesium in an electrochemical series, you're going to find that minus 2.38, and if you looked up aluminium, you'd find that as 0.8. And so the magnesium goes on the top and the aluminium goes on the bottom, so the electrode potential for the cell would be the bottom value, which would be aluminium, which is 0.8, and then you would subtract from that the minus 2.38 of the magnesium, which is going on the top with the anti-clockwise rule, and then that all comes out at positive 3.18 volts. So quite a nice voltage for that particular electrochemical cell. So that's another way of working out the cell potential using the anti-clockwise rule and this version of the electrode potential for the cell. Okay, and lastly, as usual, let's just check we've covered off our learning objectives. And the first one was that we wanted to know that standard electrode potentials can be listed as an electrochemical series, and we saw the most negative electrode potentials at the top of the series, and then in order down to the most positive electrode potentials. So the most reactive metals, the ones that wanted to give up electrons or be oxidized, were at the top, and the most reactive non-metals, i.e. the ones that wanted to attract electrons to themselves and therefore be reduced themselves, were at the bottom. And that's the first learning objective I think we can remember. And the second learning objective was to be able to use the E-values, the standard E-values. Let me just put our little underground sign in there. We wanted to be able to use them to predict the direction of simple redox reactions, and I think we did, if you remember, we did the zinc copper example, and we did the magnesium aluminium example, and we also used the anti-clockwise rule to calculate the EMF of a cell. So we're okay on the second learning objective as well. So I hope that was clear, and I'll see you in the next video lesson.